Okay, welcome to Computer Networks. Today is our 9th class. We're going to start talking about homework 5 now because homework 4 is due today. Hopefully most of you are done. We can spend a few minutes talking about it in a minute. And there are these topics for in-class student presentations. Still no one has signed up for it. If you don't want to discuss them, I will actually discuss them and I'll get all the in-class participation credit. So that's kind of the plan. So if you're interested in leading these discussions, please let me know. There is a thread on Piazza where you can reply saying I'm interested on this particular topic. We're going to actually condense those discussions into the next 3 classes or so because I wanted all those topics to be covered before the exam because some of those concepts will be covered in the exam. We have office hours, extended office hours tomorrow. Everyone knows that, right? Till 1 o'clock. Okay, so we're going to talk about homework 4 and 5 just to get a sense for where you are, and if there's any discussion that will help you. We're happy to do that, and we're going to talk about transport protocols. So homework 4 is about making web servers concurrent. There's been some discussion on the discussion board about what is the right approach, what's the best way to make them serve pages really fast. We can talk about that, but before that, if there are any unexpected difficulties, problems that people have encountered.
Well, I remember the question I asked you on the Piazza about what I'm still not clear about the answer. What determines the uniqueness of the client?
Okay, so there's a question about what determines the uniqueness of the client. Are there any other questions? We can certainly discuss that.
You remember?
Yeah.
Exactly.
Yeah. Are there any other questions? No. Okay, so that's the only thing that's bugging you guys.
Approaches are kind of mutually exclusive.
Yeah. Okay, so what determines a unique client?
I think it's the IP of the client and the pseudo-random port number that the client got assigned.
Mm-hmm. But if a particular application opens multiple sockets, you're probably going to get multiple port numbers.
The IP number is be behind proxy.
Yeah.
Something like that. IP number.
Okay, so someone mentioned IP could that user could be behind a proxy. So if it is a proxy such as an HTTP proxy, then you're going to get a single IP address for many clients, right?
So in which case you could use a set cookie on the headers, but in this case, then if your approach, you're saying that let's say you launch like 10 wget processes, then the cookie will be unique for each wget.
Yeah.
Accept cookies. So
yeah.
So it will not prevent you from launching 100 wgets, but
right.
But at least it will prevent you from.
Yeah. So it's a good thing that you have discovered that this is not an easy problem to solve, partly because it is ill-specified. And a lot of the problems in real life are ill-specified. Just to make it easier for this homework, let's determine uniqueness by looking at the user agent string. That's just for the purpose of this homework. You guys all understand the potential problems behind that approach, right? For example, what if you have 2 instances of Chrome or Mozilla or something like that? They're going to send identical user agent string. But just to make it easier for this homework, let's just use the user agent string as something that determines the uniqueness. Keep in mind that just because you're using wget does not mean you can't change the user agent string. So when we're doing this testing, we can specify the user agent in the command line, and that is how we will test it. You can specify arbitrary user agent string as a flag.
Question about that?
Yeah.
So the homework said not to accept it if it's too many connections for that client.
Mm-hmm.
But you can't determine the user agent until after you've accepted it.
Yeah.
So
that's kind of the problem. So the word accept there does not necessarily mean the accept call.
Okay.
You could actually accept a connection and not serve the request, or immediately terminate the connection. That's the easiest way to do it. And thinking about resource in the server, that's certainly less resource than having to reply with a proper request. Of course, it consumes some resource to accept the connection, read the header, but that's certainly less than having to read from the cache or file and send a response. But yeah, good question. Any other questions? There was one issue that someone brought it up. I wish this was sent to Piazza. It turns out there are potential problems with rate limiting using wget, which is, let's say the server is sending a small file, in which case, regardless of what rate the client wishes to use to read the data, the server might be able to flush everything to TCP buffer and close the connection, because the server is going to close the connection once it flushes everything to the buffer, right? Do people understand this problem? The reason we want to do rate limiting on the client is so that we can have a long-lived connection. But if the file is small, then the server is going to write everything in one shot to the buffer and close the connection, and we don't have concurrent connection. And the way to solve that is by serving files that are large enough.
Can you specify small buffer?
Yeah, but it's not, you have to configure.
Oh, so
yeah. So those are some of the issues that were brought up. Any other questions? Anything interesting that you encounter? Any difficult decision that you had to make? For example, uniqueness of the client. Anything else? This is a pretty straightforward assignment if you have the web server going on. Now, what is your strategy for how you are going to keep track of which connections are active? How are you allocating and deallocating the amount of the number of connections allowed for a unique client? How are you communicating this data across the processes?
Select, so
yeah. Oh, so you're doing everything within a single process.
I figured out that the processes IO or this application is IO bound.
Yeah.
Because it's for a file server, it's best to use select.
Sure.
For
Yeah.
application, so probably threads and forks.
Right. So if you're using select, it's easier because you have all of this information probably in an array or something like that, and it's faster. Who is using fork? So what is your strategy for how you're going to communicate this information?
I use pipe.
You're going to use pipe, okay. And anything else?
I used struct and shared memory.
Yeah, you could use shared memory, yeah. Any other approaches? How about using sockets? You could do that, right? You could also use sockets if you wanted to, but that's maybe a little bit overboard. Okay. Now about homework 5. Did anyone get a chance to look at it or no? If you didn't get a chance to look at it yet, it's probably better to defer that discussion until Monday. Who got a chance to read homework 5? Okay, that's fine. We can have the discussion on Monday. And are you almost done with homework 4, or what is the status? Who's almost done? Okay, 3.
I was actually having some trouble testing it. Bayou started slowing down.
Yeah, because probably a lot of students who are taking operating systems as well as networking using their servers. It's better to test it sooner than later. It's going to be worse, I think, closer to midnight. Yeah, but you should still be able to test for correctness, even though the performance is not what you expect. All right, should we wrap up our discussion about the homework? Yeah, okay. All right, just a brief recap of what we talked about last time. We talked about flow control, and the goal here is to control the amount of data that the sender pushes to the network to not overrun the resources at the receiver, for example, buffer space. And usually this is implemented by having the receiver tell the sender, okay, this is the amount of buffer I have. And the sender can read that information and make sure not to send more than the data that will fill up the buffer. So that's the idea behind flow control. This is clearly not enough because sometimes we have resource crunch at the network, not at the receiver. For that, we need something else. What we need is something called congestion control. This is a technique that allows us to, first of all, pace the amount of data that we are sending into the network by looking at how much data the network is able to move from one point to another, not necessarily the receiver. There are three key challenges. One is determining the available capacity. It's not as straightforward as a receiver telling the sender, okay, this is the amount of buffer that is available to receive the packets. And there are multiple parties involved in setting up the network infrastructure that is between the sender and the receiver, and it's not clear, it's not so straightforward to determine the capacity. The capacity changes over time for various reasons, as we discussed last time, and we need to be able to adjust our estimate of the available capacity as the capacity changes. And finally, we need to be able to share the capacity between the flows. That's also a big challenge. So in determining how to pace the packets, we talked about just one mechanism last time. We called it slow start. So let's first look at what happens if we don't pace the packets properly. Let's say we're just using flow control. The sender is going to send packets, enough packets to fill the receiver buffer. So what we see on the left side is a graph that shows the packets that were transmitted and retransmitted as a function of time when we just have flow control. You can see that there are large gaps in packets in time axis. And why do we have those gaps? Do people remember that?
Because it fills the flow control window and then it waits for pass.
Yeah, or you might just drop a packet and you're waiting for retransmit. In contrast, if you have slow start, which is rather than sending packets to fill the entire window in one shot, you start small. You send one packet. And if that packet was received successfully, the assumption is the network is able to successfully deliver that number of packets, so let's increase it to 2 packets per round trip. And if the network was able to deliver those 2 packets successfully, maybe the capacity is slightly larger, so let's try 4 packets per round trip. So you pace the rate using that formula. And if you use that, you'll notice that these gaps have disappeared. And this is sort of counterintuitive when you think about it, because you're controlling the number of packets that you're sending. Yet you're able to send more packets in a given time. How many packets were we able to transmit in 10 seconds if we were not pacing the packets? On y-axis we have number of kilobytes. So we can just call it number of packets or kilobytes. It's about 70, right? But if we actually control the pace at which we're sending packets, we're able to send more. Does that seem a little bit counterintuitive? And that's because the packet drops tend to be very costly in TCP, because once the packet is dropped, you have to wait until the timeout before you retransmit that. And these retransmission timers tend to be long. How long is the retransmit timer? Can you guess? looking at the first diagram?
Half a second. Second. 1 second.
Yeah, it looks like a second.
Looks like about a second. So how do we implement slow start? We've been talking about number of packets, but in TCP, the way slow start is implemented is by counting the number of bytes that we've sent, not by the number of packets or segments. And that's because the capacity is determined by the number of bytes you can transmit, not necessarily the number of packets, because a packet could be large or small. So I want you to just look at this slide, for 30 seconds and convince yourself that you understand it. If you don't, we can discuss that. MSS stands for the maximum segment size. Think of it as a packet. So let's say the window is 100 bytes and our segments are 20 bytes each. Then how many segments do we want to transmit in one round trip time? It's 100 divided by 20. Okay, 5. Good. Is everyone convinced that this?
So what if you don't get the ACK in there on the last window is transmitted?
Mm-hmm.
So
Well, which line are you talking about?
1, 2, 3, 4, 5. Line 5. So you increase
So you increase the window size by MSS on every ACK.
On every ACK. What
Right.
if on the, let's say last time when you reach the cap, download, you don't get the ACK back.
So for the last byte, for example?
No, for the last transmission, the last time the window is transmitted, for the last window.
For the last segment that
Yeah.
you've transmitted for that window, you have to wait until a new ACK before you can increase the window size.
So you
The key difference, right. So the key difference between what I described earlier and what is here is what you're supposed to do when you receive every ACK. Earlier we said you send one packet, and once you receive an ACK, you send 2 packets, right? And then once you receive these 2 ACKs, you send 4. That's what we said. But that's actually not what's happening. You're deciding to send a certain number of bytes every time you receive an ACK. And the way the formula works out is what we discussed earlier, which is after every round trip, the net result is you're doubling the number of bytes you're sending. But you're not waiting until the end of round trip and then sending 4 packets at a time. You're sending additional amount of data every time you send an ACK, you receive an ACK. And we've talked about the increment after each ACK. So that's the simple representation. You receive an ACK and then you send 2 packets. And you receive 2 ACKs and then you send 4 packets. That's a simpler representation, not entirely correct. All right? So the last thing that we talked about last lecture was what happens when you go over the limit, because we're incrementing the number of bytes that we're transmitting into the network every time we receive an ACK, and at some point we're going to reach the capacity and exceed the capacity of the network. So before TCP can respond to such event, let's think about what happens to the network performance. Let's look at the top graph. On x-axis, we have load, which is the work we're asking the network to do. That's load. And on y-axis, we have throughput, which is how much work is the network able to do. How many bits or bytes of information is the network able to transmit from one point to another. That's on y-axis. Initially, when you increase the load, the throughput also increases, which is expected. Right? But what happens after some point? When we increase the load, does the throughput continue to increase at the same pace? No. Why is that? Okay, so we'll hold that thought for a moment, but let's look at the second graph. On x-axis, we have load again, and on y-axis, we have response time. You can think of response time as, okay, let's interpret response time as how long it takes to deliver a packet. Although the meaning in that paper was a little bit different, but let's just think of it that way. How long does it take to deliver a packet from one point to another? Initially, even if you increase the load, the response time did not increase that much, but at some point, it increases exponentially, right? So there are two regimes here. Let's look at the first regime, in which the response time increases slightly. Can you tell me why the response time increases as you increase the load? It's not increasing dramatically, but it does increase, right? Why might that be the case? As an experimental setting, let's imagine we have two nodes and a bunch of network links and routers in between. Why does the response time go up as you start pumping in more packets?
Just you take up more resources.
What resources?
Hardware.
What hardware is too general?
The routers, whatever. It's not the network capacity that's being exceeded.
Yeah.
It's maybe memory or CPU that's
It's
being
just
used
you can
more.
only transmit one thing at a time. So as your load goes up, eventually you're going to try and say, okay, I want to send A, while B is in the pipe at the moment.
Yeah. So there might be
Wait for
A to be transmitted, right?
Yeah.
So there could be, for example, buffer buildups on the router. A router has a set of memory allocated as a buffer where you put in all the incoming packets, and then you look at the packets, you grab the packets from this buffer and you transmit. As you start pumping in more packets, the packets might stay in the buffer for just a little bit too long. Does that explanation make sense? So that's why the response time goes up slightly. Now, why does it go up dramatically at some point?
Because you start actually hitting network capacity.
Yeah, you might start hitting network capacity. Any other perspectives to this? Why the response time goes up? Okay, so while you're thinking about it, now let me discuss a more everyday example. This is exactly how road networks behave as well. So let's think about just the response time. What corresponds to response time on the roads?
How long it takes someone to do what
Go from one point to another, right? What happens to the response time as you increase the load? So what is load here?
Traffic.
Yeah, number of
Number of
cars,
cars.
right? So what happens when you increase the number of cars? Let's let's start from empty road. Sort of behaves like that, right? Initially, the increase in response time is very slight, but at some point, it goes up exponentially. We experience this, don't we? How about throughput?
So many cars are like going through the toll booths.
Yes.
Per
So-
unit time.
So does the throughput look similar to the graph up there, or it's slightly different? It might be. Remember, the systems are not identical. They're similar. They share similar concepts, but the shape of the graph might not necessarily be the same. What do you think is the shape of the graph, throughput graph, for roads? Yeah.
I think it's similar to that.
Similar to that? Anyone disagrees?
Well, if we're talking about a toll booth, I mean, a toll booth can only service cars so fast, so
Yeah.
if traffic is really bad,
Yeah.
the line's just going to get longer and longer.
Yeah.
It's
But how about the
Probably
throughput?
Probably, yeah, for the
I think it
toll
would be
it's not
closer
gonna
to the
increase a
bottom
lot.
one, wouldn't it? It would be, like at one point it would just shoot to the roof. The traffic would
So that's you're talking about the response time, right?
Yeah.
But
the
how
toll
about
booth
throughput?
is more-
Well, yeah, I'm saying it would look more like that
Yeah.
because
No, throughput
we
looks
get back
the
down.
same as that.
But will throughput shoot up though?
Well, yeah, but if you can only service like 5 cars a minute or something,
Okay.
and there's way more cars
Yeah.
trying to get through that toll booth,
Yeah.
then I think it would at some point.
Yeah. But you will continue to process 5 cars per
Well,
minute,
just
won't
the
you?
constant.
Until
Right.
somebody's car stalls.
So.
Until
If you've
run out
got
of
enough
cords, you run
congestion,
out of
then
chain,
other
then
problems
you
start
get no throughput.
Yeah, but I want to convince you that the top graph stays flat. So regardless of how long the line is,
yeah,
the toll booth will continue to process 5 cars per minute in
Right,
that case.
right, okay.
So you're convinced?
Yeah. I see.
Okay, good. Any other question about these graphs? No? Okay. All right. So now the question is, so we now understand what are the consequences. So how do we deal with congestion? So we need to reduce the rate. And we already do that on the roads to some extent. We try to meter the entrances. Similarly, we need to control the number of packets that are going into the network. That is what we need to do. That's the high-level idea. But before we talk about the specific techniques that TCP uses to control the number of packets going into the network, let's think about let's try to characterize the network that is overloaded. We might have heard of the word equilibrium, right? So we actually describe a certain state of the network as a network in equilibrium if the number of packets coming in is equal to the number of packets going out. It's called conservation of packets. And why is that important to think about conservation of packets? Why is it important to only inject as many packets into the network as there are leaving the network? What happens if we disturb that balance? Let's say we have a control mechanism that for every packet that exits the network, it introduces 2 packets. What happens if you have a flow control like that?
We get to the right side of that curve.
Yeah, at some point, we're going to be very congested. Let's say we have a control protocol that injects 1 packet into the network for every 2 packets that exit the network.
You end up not using a bunch of your
Yeah, we might underutilize the network. So that's also not desirable. So we roughly want to send 1 packet into the network when we know for sure 1 packet has exited the network. That's the rough goal. And if a network satisfies that property, we call it a network in equilibrium. Does that make sense to everyone? Okay. So now the question is, how do we implement or design a control algorithm that tries to maintain a network in equilibrium as long as possible? That should be the goal in that case, right? First of all, we need to find the efficient point in the network, and once we get there, we want to maintain the network in equilibrium. That is what we want to do. In order to bring the network back to equilibrium from a congested state, we need to, first of all, have a reliable way to detect that there is congestion. Right? Because a congested network, that's clearly not a network in equilibrium. So we want to bring it back down to equilibrium. But before we make this decision, we need a reliable way of knowing that, okay, we have a congested network. And it requires some kind of signaling mechanism. The network needs to tell the sender, okay, we're in a congested state. What that means is you're sending more packets than the network can process. And the signaling mechanism that is used in TCP is packet loss. So how does the sender know that a packet has been lost?
It never receives an ACK.
Yeah, if the sender does not receive an ACK, then the sender knows that the packet has been lost. And that packet loss is taken as an indication of a network being in congested state. So what's the problem with that approach?
There's other reasons you can lose a packet other than network congestion.
Yeah, exactly. So that's a concern with that approach. Because there could be other reasons why we might have lost a packet, but we're going to interpret that as network congestion. But for the most part, these networks are very reliable, and we typically don't go wrong if we assume that whenever there is a packet loss, it's due to congestion. We're mostly talking about wired networks. Now, what's the problem in wireless networks?
There's more interference.
Yeah, so the other reasons why we might lose packets are more dominant in wireless networks than in wired networks. For example, there is more packet corruption in the air. So if you use a standard TCP that uses packet loss as an indication of congestion, we could make mistakes in wireless networks. And what is that mistake? What's the consequence of making that mistake?
You use a lot less of the pipe.
Yeah, we might reduce it. We might reduce the rate. Right? Because we're using packet loss as an indication of congestion. And let's say the packet gets lost for reasons other than congestion. Then TCP is going to try to reduce the rate, and we will end up underutilizing the network. So now we know how to detect if a network is in congested state using a particular signaling mechanism. And now we need to decide how much to reduce the rate. The algorithm typically used reduces the rate in a multiplicative manner. We will get to the details of what that means. Actually, no, we'll just talk about it here. So there are many ways in which you could reduce the rates. Can you suggest some ways? There are many ways, right? What are some of the common ways you can think of? So you're sending too many packets, you need to reduce the rate. You might reduce by 1. That's a perfectly fine algorithm. You might reduce by 5. And then reduce by 5 again, and then 5 again. So that's one way. We're reducing by a certain constant, right? So that's called additive decrease. What is multiplicative decrease, if you had to guess now?
You're dividing by some percentage.
Yeah, you're reducing by some fraction. That's multiplicative decrease. TCP chooses to cut window in half. Is that multiplicative decrease or no?
Yeah.
Cutting the window in half. Why is it multiplicative decrease?
Because we divide by 2.
Divide by 2. Okay, good.
Oh, wait, so back to remember last class I mentioned if you reach like 5 gigabits or some megabits,
Mm-hmm.
then the limit is 10, you go over.
Mm-hmm.
So it's going to go over, and you could potentially transmit at 9.9.
But you're going to go down to
Or
5.
it's going to go back down to 5.
Yeah,
It's
so
going to use half the capacity.
yeah, so continuing on the example from last lecture, we had a sender sending at 2.5 and then 5 and then 10. The capacity is 10. And the sender is going to try to send at 20. It's not going to work. And the sender is going to reduce the capacity to 5. That's what we're talking about using this particular algorithm. You already see the inefficiency here, don't you? Yeah. It's actually worse than that. I'll tell you in a little bit. The window gets reduced in half, but you actually do a slow start. Start with one segment again.
No, but you continue to build up until you reach the capacity. Right?
So I'll get to that. I think it's easier to explain when we have the diagram there. So we clearly see the problem here, right? there is some capacity that is going to be in the network we will not be able to use. And it's because of that reason the sender is going to, again, increase the rate at which it's sending the packets because we don't want to underutilize the network. So we're going to reduce the capacity in half, but we need to be increasing the rate all the time. And the reason is the network does not tell the sender, okay, here's the remaining capacity. We've decided to use a particular signaling mechanism to detect congestion, and that's the only signaling we have. So we're going to continue raising the rate at which we're sending the packets to see if we hit the limit, because we don't want to underutilize. There's a nice way to visualize the consequences of running this type of control algorithms using something called phase plots. So on this plot, on x-axis, we have flow rate for flow A. And on y-axis, we have flow rate for flow B. So we can think of these as two different senders trying to send packets in a single link. So that 45-degree line, if there is any flow rate allocation that falls on that line, that means the two flows have achieved exactly the same rate, right? So if our flow rate allocation, we can represent that using a point on this graph, and if that point falls on that line, we call that fair allocation. There's another line here that tells us what is an efficient allocation, efficient rate for the network. So the network has certain capacity. The combined rate, if it falls on that line, we're operating at exactly the most efficient point. We're using up all the capacity that the network has. So that's the efficiency line. Why is that line shaped in that particular way? Can anyone tell me? And that's actually very important to understand what happens in the next slide. Let me ask you a question.
Because the more you're sending with one, the less you're going to be able to send with the other one to keep it balanced, basically.
Exactly. It's basically A plus B.
It's like a vector.
Yeah, exactly. It's the total sum that is bounded, not necessarily the rate at which a single flow is able to send when we're thinking about efficiency of the network. Let's say we have flows A and B, and A uses up all the capacity, B is completely starved. That might still be an efficient allocation. Not necessarily a fair allocation, but that might be an efficient allocation. That is our goal usually. We want to be fair across the flows and efficient, right? That's our goal. Any question so far? The fairness line as well as the efficiency line? Okay. So that's our goal. Whenever we have TCP changing the rates, we're trying to be fair across multiple TCP flows and efficient, right? So far, we've only talked about efficient because we assume there is only one flow, but we want to be fair as well, and that's the additional dimension that this graph brings in when we think about how TCP works. Okay. Now let's say initially we have that particular allocation. What that means is at a given time we have flow B sending a lot more packets per second than flow A. That's what it means, right? That particular allocation. If we have multiplicative decrease, what would the next point look like? What would be the angle?
It'll be the same angle, but halfway closer to the origin.
Okay. Why would it not be parallel to the fairness line? So that's something to understand. You are right. Multiplicative decrease will point towards the origin, which is what you said. But why is it not parallel to the fair line?
Because you're decreasing the flow flow rate of A and B?
Yes, but even if you do additive decrease, you would decrease for both flows A and B. But maybe it's easier to explain that in the next sequence. But as you suggested, when we have multiplicative decrease or increase, we're going to move along the line that connects these points to the origin. Does the ratio of the flows A and B change when we have multiplicative increase and multiplicative decrease?
No.
It does not, right? That's something important to remember. Now, let's start with that particular flow rate allocation. And we have additive increase. It actually looks like that. Why does it look like that? Why is the angle different? Does everyone notice the difference in angle? So why is the angle different now? This is important to understand.
Because here the ratio does change, right?
Yeah.
Since they're both being decreased by the same absolute number, but one's bigger than the other one. So.
Yeah. So why is that line 45 parallel to 45-degree line that we have?
Because they're
It's not necessarily fair. Why is it?
right. Because it's like what you said. The rates are different. So
Yeah.
taking away like 5 from the higher rate isn't. Yeah.
Yeah. No, continue in that direction. So you want to take.
away 5 from the higher rate. It's not as much of a difference if you take away from the lower rate.
Yeah.
So it stays.
Right. So, but I want you to continue in that with that thought. So you want to take away 5 from the higher rate,
Right.
and you also want to take away how much from the lower rate?
The same 5.
Same. Now, if you subtract 5 from x and 5 from y, what is the angle made by that line? Because that's what's happening here, right? So what should be the angle in that case? It's probably 45, because both the sides are the same here. So do people understand why these angles? I mean, it's a little bit subtle here, because if you look at it at a high level, it all looks like some lines moving back and forth, but there's an important story behind that angle. So if you have additive increase and additive decrease, you're going to oscillate in that line parallel to the fairness line, to the 45-degree line. Okay. Now we all know how those particular control mechanisms work. If you want a system that converges to fair and efficient allocation, what kind of strategies should you use?
Multiplicative decrease, additive increase.
Why is that?
Because it'll sort of zigzag inwards.
Mhm.
It becomes more fair when you do the multiplicative decrease, and then the additive increase preserves the fairness.
So do people understand? It's really easy to explain using that graph now. Because that's the only way you can converge, you can move towards the fair line as well as the efficient. I want to talk about one other point about these graphs. All the points, all the flow rate allocations, that's what we're talking about, that are on the left side of the efficient line leave the network underutilized or overutilized? Underutilized. And if the network is underutilized, what should the control algorithm try to do? Increase. And is that what it does? It does, right? It pushes the point on the other side. Because we don't know exactly what that efficient point is, that is what we're trying to find. So all the points on the right side of the efficient line, we have a network that is congested or operating beyond its capacity. And when you're operating beyond its capacity, what should the control algorithm do?
Reduce the flow.
Yeah, reduce the flow. And ideally, you would want to get stuck exactly at the efficient point, but that's not what happens. You undershoot. Okay, any questions about these phase plots? Okay.
Actually, doesn't doesn't that risk that you'll significantly underuse the network if lots of connections are always being added?
Yeah,
Because you'll
Mhm.
you'll be having that multiplicative decrease all the time, and your additive increase won't keep up.
Yeah. So the question was, if there are lots of flows and if you're decreasing your rate multiplicatively, don't we risk underutilizing the network most of the time? And yes, if we just use that basic algorithm, that could very well what we might observe. So we need to do something smarter, obviously. And I'm not sure if we talk about that today, but maybe in next lecture. We're going to talk about some of the more advanced control algorithms that have been used. All right. So now we know what that particular control strategy is called. Let's summarize the two states of TCP rate control algorithm. So initially, we are increasing the rate at which we're sending the packets. So that's the increment formula that you see on the slide. I think we all understand that. What is that phase called? There is a name for it. When TCP is increasing the rate, what is it? What is that phase called? It's called slow start, right? And when there's a packet loss, TCP actually does a multiplicative decrease. We don't want the decrease to be too small, up to a certain amount, for example, MSS. And finally, we want to back off exponentially. I think it'll become clear later. If there are no packets in flight, how do we even know how long we're supposed to wait? That's kind of the question there. So this trace, you should be able to interpret this trace now. On y-axis, we have amount of data sent. On x-axis, time. If we have additive increase, we expect these lines to be straight, going up, right? Now, what are those drops that you see there? That's the multiplicative decrease part. And once you decrease the rate, you start probing again, you start increasing the rate again. Any question here? So this is what it would look like. This is the plains TCP. I mean, we don't use TCP that works like this anymore. But if we use TCP that uses the basic original algorithm, this is what it would look like. So here is what TCP looks like based on all of the discussions we've had so far. So it has two states called slow start and congestion avoidance. During slow start, how do we know we're in slow start? So there is some kind of threshold called slow start threshold. And when we're in slow start state, we're increasing the window size. And once we hit the congestion, what we do is we reduce the window, right? And once we reach that threshold, we actually don't increase the rate as fast as we did when we were in slow start stage. So this is the example that someone mentioned earlier, which is once we've hit the limit, let's say 10, we're back down to slow start. That is what happens. But once we hit 5 while increasing the rate, rather than doubling every time or every round trip time, we increase it just slightly, which is the increase that is shown in this formula under congestion avoidance. So those are the two different phases. Is that clear to people? Once we reach that halfway point, we increase the rate slowly. until we reach that halfway point, we actually double the rate at which we're sending packet every round trip. And just to simplify the discussion, if we want to talk about number of packets, we can say until we reach that halfway point, we double the number of packets every round trip. And once we reach that halfway point, we increase the number of packets by 1 every round trip time. That's the simplification. That's called congestion avoidance stage. So we have slow start, we drop the packet, we do slow start again, and once we reach the halfway point, we start increasing the number of packets very slowly. All right, so let's take a very quick break, and then we'll continue our discussion. Yeah.
Is there a sysadmin in charge of cleaning up IP?
Are there a lot of sockets?
There are a lot of old processes on there. Like I did a
Is this from-
EF, and there was like probably at least 100 processes that had their start times in 2011 and were processes that said like assignment 3 from some fall 2011 class.
Maybe we should ask them to reboot it.
Yeah,
They're the best, right?
it probably wouldn't hurt.
We need to make sure no one's using it at that time.
Yeah.
Yeah. Why is that?
Because you said you want to use his homework.
Oh, I already talked to him. Actually needed your help at 2:20. I actually needed your help carrying something.
Okay, sure. Right now?
Immediately after the class.
Okay.
Are you going to be here or in the lab? You're gonna be-
Also,
Okay. Okay, I think we should start. All right. So we just realized that it's not that easy to find the right rate at which you should send data. It's not an easy problem, and it's particularly made hard because the network does not give us feedback as to what is the right capacity. And even if it did, there could be competing flows competing for the same resource, and they might not play by the rules. So it's a hard problem regardless, even if the network did assist us. Now let's think about losses. How to detect the loss? Because we're talking about reliable transport, we need to be able to take the loss so that we can retransmit the packets that have been lost. First is timeout. We sent a packet with sequence number 5, and we estimate the round trip time to be, let's say, 1 second. And we wait for a second to see if we receive an ACK for that sequence number. Right? So that's called timeout. Is there any other way? And it turns out there is. You could infer losses by looking at the gaps in acknowledgements. So let's say you've transmitted packets with sequence numbers 1, 2, 3, and 4, and you received ACK for, let's say, 1, 3, and 4. What can we infer? Probably packet number 2 was lost. It could be wrong. Why could it be wrong, that inference?
Packet number 2 would have just been delayed.
It may just have been delayed. Any other reason?
The ACK for it could have been lost.
Yeah, the ACK could have been lost too. In TCP, duplicate acknowledgements are typically used when certain segment is missing. For example, going back to the scenario that I presented, so the transmitted packets are 1, 2, 3, and 4. Let's say 2 was dropped. Then TCP will actually send an ACK for 1, and then 1, 1, 1. So the duplicate ACKs could be a way to signal that there was a segment that was lost. And the usual number is 3 duplicate ACKs. If we receive 3 duplicate ACKs, then that means the segment was lost. Let's look at pictorially what we've covered so far. And this shows what timeouts are. For example, right after slow start, the line flattens, as we can see, and there is a gap in the packets that we're sending. This graph doesn't show that. It shows that the window stays flat and then window drops, right? So that's the timeout. And once TCP determines that there was a packet loss, then it's going to start at slow start. That slow start threshold is half the maximum window size in which it is able to transmit successfully. It's going to do slow start until that threshold, and it's going to increment the window very slowly. Additive increase. And there's a timeout again because the packet was, the acknowledgement was never received. And why is the slow start threshold lower the second time? Because it's always set to half the window size that resulted in successful transmission. That's why it's lower. So next time we're going to start with one segment again, and we're going to use slow start algorithm to get up to slow start threshold. Once we reach that threshold, we're going to increase the window size, which determines the rate at which we send packets, very slowly, additively. So for this mechanism to work properly, we need to know how to set the timeout. If we don't know what the right timeout is, we might make mistakes. For example, we might misinterpret a packet that was delayed as a lost packet. So it's very important to be able to estimate the round trip time accurately. It can be variable, just like the network capacity. It can change over time. Why would round trip time change over time? Let's say the network itself does not change. The physical infrastructure in the network does not change. But I'm arguing that round trip time can still change. Can you think of a reason why it might change?
Size changes with load.
Yeah, it might change with load, right? Because we might the buffers might have small number of packets or large number of packets. We're going to explore in homework 5 how to come up with an estimate that tries to track the physical phenomenon as much as possible. One of those techniques is called EWMA. The other technique could be just taking an average over 5 seconds, but what's the problem with that approach? It might not be representative of what happened in recent past, which might indicate what will happen in recent future, right? And the idea is we estimate what the round trip time is. We make some measurement and we compute an estimate based on those measurements. And we use that estimate to set the timeout value. If we don't receive an ACK during that estimated round trip time, then we know that the packet was lost, if the estimate is accurate. This is the standard EWMA formula that you've already seen. Just want to ask you, how do you sample RTT in TCP? Because this formula requires that you have a way to sample RTT. How do you do that? For ACKs that you're receiving, you can just record the time you transmitted that data segment. And once you receive an ACK, that gives you an idea for what the RTT should be. So that's the sample. That's the most recent sample of RTT. Once you have that, you can maintain this type of estimate, and timeout is just 2 times the estimate. Let's say so there are some problems with this approach of estimating RTT. Let's think about just sampling, sample RTT. Let's say you had to retransmit a segment. Does that complicate the computation of RTT? Yeah, because when we receive an ACK, we don't know if it was an ACK to the first transmission or the retransmission, right? So we don't know. So the solution is pretty straightforward. You only use the samples that correspond to segments that were not retransmitted. Second problem, it does not take the variance into account. For example, RTT could exhibit some behavior where the average is, let's say, 5, but there's a lot of variance over time, and it's not converging. Let's say over a long time, it just oscillates. This type of estimate does not take that into account, right? It gives you some sort of average. It'll try to track the samples to the extent possible, but still gives you some form of average. Does not directly take into account the variation. And the solution to that particular problem is to take into account the variation explicitly. You basically maintain 2 different estimators. One, the sample, the other one, the variation. And the timeout is actually sum of those 2. So why is this better than just using the first estimator? Because it also tells us what's the expected variation in RTT, right? For example, let's say if I told you, average speed, on the freeway is 50 miles per hour. That does not mean there are no cars going at 10 miles per hour, right? But if I told you average speed is 50 miles per hour and the expected variation is a certain amount, then that actually gives you a lot more information about the distribution that you should expect. And it turns out this is a particularly efficient way to maximize the amount of information that you have to determine what the right timeout value should be. You not only take into account the average values, exponentially weighted moving average, but also the variation. Let's look at what happens when we use just the first estimator. So those dots are the RTT samples. You send a packet, you receive an ACK, and you record the time. Saying, okay, it took, for example, I don't know, 4 seconds or 2 seconds or something like that. So you're recording just the round trip time. The solid line is the estimate. So why is the estimate so high sometimes? I think we're using double.
Oh, okay, you're not taking variance.
Yeah, but you're not taking into variance. Let's get into that later. But this estimate tracks the samples, doesn't it? It does. That is what it's designed to do. But if we set the solid, if we use the solid line to set our timeout, we run into some problem. Can you tell me what problem we might run into around 60th second? I think it's around 60th second, yeah. Between 50th and 60th second.
Getting a timeout on a packet that maybe got there.
Yeah. We might have spurious retransmission. What's happening around that time? Let's say, around 50th, 60th second. If you look at the samples. So there is a high variation there, right? For example, most of the samples are within 2-4 seconds. That seems like the overall trend, right? But just around that time, there's just a high variation. There are these samples that deviate a large amount from the overall averages that we've been seeing. And because this estimate is an average, it's going to try to smooth that variation. And that's the reason why the estimate does not jump as high as it should. If we take into account the variation in the estimate or the timeout, we actually are able to avoid the spurious retransmissions. And this is the new algorithm, new as in new when it was proposed a few decades ago. that solved that problem.
Are we still getting spurious retransmission on that graph?
We might, right? We might still be getting.
Same exact spot.
I think there might be fewer spurious retransmission. Yeah.
I'm not sure it reduces.
I think there's more.
Just
Just
more accurate estimate of RTT.
So I think, but there is a danger that because of the high variation, there was a danger that we might have gotten more spurious retransmission, which this new solid line envelopes. We at least noticed that, right? I think you bring up a good point that maybe we're not necessarily reducing the number of spurious retransmissions in absolute numbers here. But I'll suggest yet another way to solve this problem, which is we can make the estimator, just the top estimator, more agile by changing the weight. If we use a very high weight, let's say close to 1, what does that estimator do?
It just sets whatever the sample is basically.
Yeah, let's say I use an alpha of 1. The estimate becomes exactly what the sample is. Will that solve the problem here?
Definitely not.
Why not?
Because then the next packet that comes, if it takes longer, then you're screwed.
Yeah, exactly. So that's the problem, right? When we have a very high RTT for a particular sample, it almost seems like it'll solve that problem because our estimate becomes exactly the same as the sample, right? But the next time when we have a lower RTT, our estimate becomes that lower RTT, and then we have a problem. So we want that smoothness. All right. So just one small concept before we end today. As we've seen in this diagram, whenever there is a packet drop, we reduce the window size and then we do slow start. Can you think of a way to, first of all, what is the inefficiency here? We're potentially underutilizing the network again, right? Can you think of a way to improve on this?
Not do a slow start.
Okay, so where would you want to start?
Where the
Slow
where the cutoff, where the halfway point is.
Yeah, so you want to start there?
It actually makes sense because modern networks are fairly fast, so we might as well assume that the network is going to be.
Yeah.
And we don't use that.
Right. So that's called fast recovery. So rather than do slow start, you basically retransmit the missing segment. Because we need to do that because we had to reduce the rate because there was a segment that was missing. So we retransmit that, and we stay in congestion avoidance mode at half the size. Just looking at it as a diagram, so we have 5 data segments that were transmitted. The second one was lost, and we receive a bunch of dupacks. Right? The acknowledgement is sent for the packet that was actually received. The sender can infer that segment number 2 was dropped. And it's going to just transmit that segment. Why is that called a fast retransmit? What is so the opposite of fast retransmit is what? So what is a slow retransmit? What's that? Can you say that louder? When you retransmit everything. No, but I think we're just talking about time.
Because you're not waiting for timeout.
Exactly, you're not waiting for the timeout. That'd be if you wait for the timeout, it's not officially called slow retransmit, but that's what it is. Why is this fast, or why is it faster than waiting for the timeout?
Because as soon as you see that you didn't get them all,
Yeah.
you just send it.
Yeah, and we're actually sending and receiving these packets a lot more quickly at a completely different magnitude in time, or a completely different time scale than the timeouts. And that's what is called fast retransmit. So once you do fast retransmit, then you do fast recovery, which is stay in the congestion avoidance mode. So if you put that together, this is what the diagram would look like. At a slow start, you drop a packet, and you detect that quickly, right? Using the dupacks. And then rather than going down to slow start, you actually stay in congestion avoidance mode in which you're doing additive increase. All right. So here's the last slide that tries to capture the discussion that we've had so far. The first problem or the challenge is determining what is the capacity. For this, we don't want to do additive increase, as we said. We want to do exponential increase. You receive an ACK for 1 packet, you send 2. I think earlier I made a mistake saying in a multiplicative increase. In this beginning part, it's actually exponential. We go from 1 segment to 2 to 4. Right? That's not multiplicative increase. That's exponential increase. But we call it slow start. So just to keep that in mind. Slow start is actually not slow. It's an exponential increase. And later, once we know that we've hit the capacity, now we need to actually do a better probing for what the most efficient point is. At that point, we do additive increase. We detect congestion using packet drops. That's the signal, right? If we drop a packet, we assume that's due to congestion, not because of other reasons. one easy way to detect if there has been a packet loss is if there are timeouts. We sent packet number 2 certain time ago, and this is clearly taking much longer than the estimated round trip time. Then we can say, okay, the packet has been dropped. Another way to detect congestion is by looking at duplicate acknowledgements, certain number. And we also talked about fast retransmit and fast recovery. This allows us to reduce the rate when we've gone beyond the rate the network can support, but not to reduce it too much to underutilize the network. What that means is try to get back up to the efficient point as quickly as possible. So those are the challenges that we talked about today. And we'll talk more about transfer protocols in the next lecture.